Okay, let's start. Maybe Emerald, you said you can see the screen?
Yes, I can see the screen.
Okay. So welcome to the last lecture of Rob 101. It's been a great journey. We'll talk about it later at the end, see if you have questions. I'll try to leave some time we can talk a little bit. For today, I decided not to prepare slides because we want to run code. So there's only one notebook. It's called Convolution. It's in the notes from lecture fall 2021. If you download this notebook, you can upload it and run it on IllumiDesk or locally. Now, because if you remember last time, I had some problem. I couldn't run the code. It turned out it was actually something very easy because I updated my Julia kernel to from 1.4 to 1.6. I had to update the packages. And if you run it locally like me, so that's the nice thing about Julia as a programming language. You can just import your package, and if then you run package update, it will update it for you. Now, not every language is like this, having a centralized package maintenance that you can update and download automatically. This is very nice. So when I did that, I could run the code on this laptop too. Now, why I'm telling this to you now? Because now it's 1.6, maybe 3 months from now it's 1.7, right? And you decide to maybe upgrade. So Julia is still young, and you probably want to see what's new in newer versions. So you don't see much now because I did it at home. But so by the way, this is a terminal that you can just run code and do everything. That notebook is more like a friendly version of running code and typing text. So I will close this, and I will run Jupyter Notebook. I'll try to run the code again. It should work. It worked right before the lecture. So I will run the code from last time because I want to show you the randomness. When I generate data set, it's not the same shape every time. It can be different. Then we will talk about a very important topic in today's research called convolution. So you need to add OSQP and Compat. I have them already, so I don't run this line. This is the block this is the soft margin classifier. When I run this, I'll get a bunch of points. One of them is the other side. Then I can run the classifier and solve the QP. This is still running. So now I have the QP. This is a soft margin, so there are a lot of slack variables, but the first three, if you remember, that was our line. And then I plot the line in the regressor form to see I need to load. Oh. I thought I ran. I think I didn't run this block for plotting. So it was complaining about not having the plot package. And in the code, you might wonder what I'm doing with this exclamation mark. Because I have the class IDs for one class, I'm negating this to get the opposite class. And the dot means do it for every entry of the array. So it's actually nice. It's a very It's a terrible data set. They're super blended, right? And the soft margin classifier is doing a good job. I mean, there's no escape from this, right? So with great power comes great responsibility. It's very dangerous. You assume your model is the reality, and then you're going to make decision that will affect people's lives, right? There's a lot of drama in face recognition. You create a data set that's not representative of population, and all that story. So there's, I think, a great course developed by Professor Ben Kuipers, Ethics in AI. These are more modern topics. Ethics in artificial intelligence and robotics. So we're going to have great power in our hands. So we also started thinking about the impact of these technologies that we develop on society. So never assume your model is the reality. There's an old saying, people tend to fall in love with their model. If you work long enough with a model, you start believing that that's the reality. I can tell you that. So now we're going to run the Gaussian version. That was the nonlinear case, mapping to the feature space. We talked about a feature vector and how in the kernel methods, this type of problems we define implicitly a feature map using that radial basis function. We also talked a little bit that in neural networks, we learned that feature map. I'll tell you another difference in the convolution when we reach to the end of the lecture. So now this is our problem. It's clearly not possible to separate them with a line. We have tons of variables now. If you remember, it's not 3 weights, it's n plus 1, n number of data points, and n slack variables. What am I missing now? Did I define the regressor matrix? Here maybe. I'm rerunning everything I can. It's like a terrible, that's like reality, right? Instead of reading one-line error, I'm just running everything because I know it will work. You should just be more patient and read the line, see what it's complaining about. That's why debugging code takes longer than expected. Being super impatient. Okay, so it worked. But it works, so I got a reward. I will do it again next time. Let me run. So the contour plot will give you this decision boundaries, these level sets of the function. You could choose any of them in principle, but we take the sign. We're going to do positive one class, negative one class for the model. And when you do that, you get the classification. So if you rerun it again, you get different results, right? So again, for those of you who just joined, if you upgraded your Julia to different version, make sure you can run package update to get the latest packages. That was my problem last time. And then it just disappeared when I updated all the packages. Okay, so this was from last time. Let me know if you have any questions. Otherwise, I'm going to move on to the convolution topic. Again, there's a notebook on Canvas. So today we're going to talk about convolution. Convolution is a mathematical, basically, operation. It has a continuous form. Typically, you learn it in a course on maybe. I learned it in differential equation. You might learn it in a course on maybe analysis, maybe signal systems. I think you can. It can fit into a lot of courses that they have good math background. But generally is to use a verb that will not help you to understand is that you get a function and convolve it using another function, right? You're just squishing it through another function. And that will do something to it, and that's an integral. It's hard to imagine, but it's immensely useful, and it has a lot of applications. In a course on signal systems, you also learn that, or maybe automatic control, that there's an equivalent of time-space operation. You do convolution in time. You can use Fourier transform or Laplace transform to go to the frequency domain. And then the convolution, which is an integral, is just the multiplication. That's called convolution theorem. That is historically has been very useful to implement a lot of packages for digital signal processing. Julia has a package for digital signal processing. When you hear digital, means it's discrete. So what you see here is a sum. It's not an integral. So we're going to talk about discrete convolution. And discrete is always suitable for implementation on our today's computers. So the convolution of an n vector, A, and another m vector, B, so they don't have to have the same size, is another vector, and its dimension is n plus m minus 1. We typically, let's say if the outcome is C, we use this asterisk. That's the sign. This is not multiplication. This means convolution of A and B. Now, the way it's defined is using this rule. So let's say every element of C, Ck, so K can be from 1 to m plus n minus 1, is the product of two of the entries of basically A and B, but some of the indices, I and j, must be k plus 1. So Ck means grab A I and B j such that I plus j is k plus 1, right? Now it's a little, more than a little, it's confusing because how are you going to track this, right? Not very fun to think about it. But let's look into, so this is the definition of one-dimensional convolution. Okay? Let's look into an example. Is there a question? No? So when n is 4 and m is 3, let's see if we can find a pattern here. When c is 1, we have a1 times b1, right? 1 plus 1, 2. There's always 1 more than the index of c. When c2, now you need to sum over all of them, right? Not just one term. So when c is 2, we have two possibilities. a1, b2 plus a2, b1. What about c3? We have three possibilities, right? A1, B3, 1 plus 3 is 4, 1 more than 3. A2, B2 plus A3, B1. What about C4? There should be more, right? C4 is A2, B3, but we could have A1, B4, right? But B4 does not exist, okay? So when the indices are out of bound, it's just 0, okay? In this line, we could have A1B line 4, A1B4, but B is a 3 vector, so it's 0. So that's extra condition that the entry must exist, otherwise it's 0. So because the only possibilities are now A2B3 plus A3B2 plus A4 times B1, because A is a 4 vector. We go to C5 and C6. Now for C6, you see that we can only do A4 and B3 because it's, every other possibility just does not exist. Okay? Now, looks like impossible to remember, right? You probably want to code a function and then just never look into it again. And you're right. That's exactly what we want to do. Nobody likes to think about indices again and again. But notice a pattern here that as if it's backward, right? We have, let me use drawing. So when you do dot product, it's A1 times B1 plus A2 times B2 and so on. But here, it looks like it's somewhat flipped. We have A1 times B2 plus A2 times B1. So if I have like I mirrored B, right? Instead of having B1, B2, mirror it with respect to this line, right? You get a new vector, and you can call it B2, B1. I can call it, I flipped it vertically here. Or if your vectors are row, you can flip it as if you applying some sort of rotation or reflection. So when you do that, then the dot product makes sense because this is A1, B2 plus B1. So I'm telling you this because when we go to 2D, it's so much harder to think about it, but this is the reason later I will flip one of the matrices. Because when you flip it in 1D, you can talk about the dot product now, right? Same true for C3, right? A1, A2, A3, right? We have B1, B2, B3. If you flip B, dot product makes sense. Or it doesn't have to be dot product. It can be, or it is a dot product. You can talk about A transpose B or vice versa, right? So it can be a vector multiplication. Does it make sense for C4? I wanted to give you intuition why we will do that, but I haven't written here. Does it make sense? Does this rule make sense for C4? What does it take to have, I have A2 A3, A4. On the other side, I have B3, B2, B1. It makes sense, but it's not so obvious, right? Because, well, you need to pick a certain part of the vector A, right? Not the entire vector. And that's exactly what we will see in the first example. So if I have a long vector A, and there's another vector B, the convolution, what it will do, it starts from here and move one at a time, right, forward as a sliding window. So you move one block at a time. This is a visualization of this somewhat abstract equations here, right? This window, B, is moving one block at a time, but each time to calculate it, you pick the overlap, right, which is another vector of 3 elements, flip your vector B, and then take the dot product. And that will give you the convolution. So that's easy to understand. We know how to code it and implement it. Otherwise, just writing if and else, check if the sum is k plus 1 not, that doesn't sound like a good way to implement it.
So a little bit confused how you're figuring out the specific indexing of A or B to choose out of the bigger A.
So the rule is, so the question is, the indexing is confusing. What's the rule? So the rule is, the definition of convolution is that, here, K, right, CK, K is from 1 to m plus n minus 1. This is the convolution of an n vector by an m vector, right? Now, the rule is that you pick and sum all the elements such that I plus j, right, equals k plus 1. Okay? So the first example here, we see that this is I is 1 and j is 1. 1 plus 1 is 2, C1, right? Now you cannot find any other 2 elements, A and B, that satisfies this condition.
So is it kind of, as opposed to, I was asking kind of about an A234 and then B321, are you doing that just based on going through and seeing the possible combinations?
I'm going, in this case, I'm sweeping over all possibilities, and these are all you will find, right? It's like brute force. Just go over all the possibilities exhaustively, and this is what you will end up with.
And then for bigger ones, that's why we create functions to do it for us instead of...
Yeah, and you can imagine, I mean, if you have a vector of 100, even if it's 50, 10, it's really difficult to do by hand, right? The chance of making a mistake is more than chance of success at that point. So this is the rule and the definition. Then I came up with that intuition that it looks like we saw a pattern here, right? And then we realized that if we flip B for all the valid indices, right, and take the dot product, it does give the desired result. And for C4, we realized that, well, the length of vector A should match vector B for all the indices that will satisfy that constraint. So it turns out, with that logic, you can come up with a visual way of calculating the convolution. And I'll try to visualize it here for you. I have a vector I'll write it as an array, as a block of array. Then I want to do a convolution by a 2 vector, right? This is 1, 2, 3, 4, 5. We have 1 and 2.
Why did you align it like that, like as opposed to putting the 1, 2 directly underneath?
Why did I write it?
Like you aligned it so that there's like only one of them, like kind of over each other?
Well, yeah, because I want to sweep the 2 vector by going through the other vector, right? So step 1, bear with me. Step 1, k equals 1. I need to flip the other vectors. It's going to be 2 and 1, right? So the only matching part is this. So I guess C1 is A1, B1. I move 1 step forward, right? Step 2, I'm gonna, K is 2, right? C2 is A1, B2 plus A2, I can write here, B1, right? Next step, let's move forward. 2, 1, this is my vector B, this is my vector A. So the next one is going to be between 2 and 3, right? Because C is 3, you're going to have 2 and 2, 3 and 1. So that's completely captures the convolution. That's how it's done, right? Now you're going to go to 2D, you have to move along 2 directions. You're going to go through 3D, you probably don't want to visualize it, trust me. You want to use a library that people sat down and discussed it for hours, how to implement it. But hopefully this visualization, I wish we could make some craft to move vectors into each other and make convolution. Or maybe we should make an animation. I'm sure there are animations on the internet too. But you can make a convolve a vector A using B like this, okay? That's the idea. So hopefully this makes this scary indexing here more approachable. It's one of them is flipped and it's going through the other one. Is everybody comfortable with this visual way? Because this is equivalent of that equation. Actually, the visual way, you should already have some idea how to write a function about it, right? Take 2 vectors, flip one of them, loop over your vector, right? And then keep taking the dot product for every entry of the output. See no questions in chat? We are now 1D convolution masters. Now I'm going to clear this page. All right, we're going to do this one by hand. Let's say I have a 3 vector here, 1, 0, negative 1. I want to calculate this convolution with another 3 vector, 2, 1, negative 1. So we already know the output should be 3 plus 3 minus 1, which is a 5 vector. If you follow the rules, it's just like dot product calculation, multiply, add, then you get your vector like this. So it increases the length of your vector. You're free to chop the sides off to make it 3 again, but the true output is bigger always, right? Some packages allow you to specify that I want the same size as the output. MATLAB does that. But the actual convolution size is bigger than each of the inputs. Now, this seems useless, but I'll try to convince you that with a simple example that this is already very useful. Some properties of convolution. The convolution is symmetric. This is very nice because the drawing that we had, it doesn't matter if you take A and move B, or you fix B and move that bigger vector, right? The convolution of A and B is the same thing as the convolution of B and A. So you don't have to think about it. The order is not important. It's also associative. If you convolve A with B and then convolve the solution with C, it's the same thing as convolving A with the convolution of B and C. So that makes it even nicer. Another property is that if the convolution is zero vector, one of them must be zero, because that means everything that you calculated in those dot products, right? It's just giving you zero, so one of them must be zero. We can guess that already. Why? Because the dot product is only zero, right? If one of them is zero. Or even from A transpose B is zero only if A or B is zero, at least. Convolution as a linear map. Another way to think about convolution, which is maybe makes sense now, because if I can do this step by step using vector-vector multiplication, maybe also I can stack this into a matrix and do one time a bigger matrix times a vector multiplication. And that's in fact possible, which makes it I find it easier whenever there's a just big matrix. I multiply by vector. That's where I'm happy. For the rule to make such a matrix is this. Again, you can think about it, what it means, or you can build one and see what it means. So that rule is telling us, because it's symmetric, right, you have the option to construct this matrix with B or A, your choice. Let's say with B, consider a matrix of what? Now, we know that the output is n plus m minus 1, right? So that's the number of rows we need in our matrix, right? And we know that if I'm going to construct the matrix using the m vector, then I need at least n columns, so I can multiply it. So that's given in the problem. So this is n columns and n plus m minus 1 rows. So grab your vector B and add it in the first column, and then shift it. And then whenever you shift it, everything else must be 0. Shift it again, and again. Oh. So it's the same vector. I'm just starting from the first row. I'm just moving it down. You could do the same thing with A. This time we have 3 columns and the same number of rows, because the output of the convolution will not change. So you can have T, B, I mean by this, it's a matrix T constructed from B times A. This is the same as T, A times B. This will give you the convolution C. Again, we have A, and A. Now, you can now go back to the rule. What was the rule? It's telling you that bi minus j plus 1, as long as it's within the bound, right? Because this is an M vector. Goes to entry ij, otherwise 0. Right? How can you prove this? Do a direct calculation. So you'll see the result is correct, and that's the proof. Now, this matrix has a name. It's called Toeplitz. Sounds like a German name. Maybe there's a better pronunciation. But Toeplitz is named after Otto Toeplitz, the mathematician who invented or used this matrix. So this particular structure that you start from that column and then move if we call this diagonal, right? It's not a square matrix, but consider this as a generalized diagonal concept. Then move your vector along this diagonal down. This type of a structure that we see is called Toeplitz matrix. It shows up, I don't know, some places in control. When I was a master's student, I was working on the optimal preview control. You want to give the reference for sometime steps in the future so the system knows what's coming up and starts acting faster instead of being lazy and having delay. And this sort of matrix would show up to somehow past, future references to the system. So it shows up in control theory, also in convolution here. So sounds like all you need to do, you need to pass your vector to construct this matrix and do a matrix vector multiplication. And that's your 1D convolution, right? Even simpler than sweeping vector through vector. Now, we just talked about 3 ways of calculating the same convolution, right? These are just equivalent. One might be better for implementation than the other one. Let's see which one I chose to implement. I'm doing matrix vector multiplication. So what I'm using the Toeplitz matrix. So let's look into one example. One example that convolution, 1D convolution is used in signal processing is time series smoothing. Imagine you have a noisy signal. I am simulating this case here. So I have a sine wave, but the actual observations I have, they are very noisy. So the true signal is the blue line. Noisy signal is what I actually observe. One example is, for example, where you can think about it maybe. Nobody invests here in the stock market. If you do day trading, this is familiar. No? Ben? No? That's good. So you're after long-term trend, right? Buy the stocks, leave it there 5 years, come back, see what happens. Well, Warren Buffett says you need to find small companies. You buy Apple, Apple is already...
Yeah, but it's less risk.
Less risk, but less reward.
Versus more reward, higher risk.
High risk, high reward.
I'd rather play the long game.
Ben plays the long game. That's very good. Can also sell the losers before the end of the year, and then sell the winners after the end of the year, so you pay less tax.
Yeah, exactly.
You can do that too. So the stock market, if you look at it every day, it drives you crazy, right? It's just going up and down, super noisy. But the trend is not that. This is a separation of signal from the noise. It's arguably the most important skill in life. But we're talking about a very simple problem here. So you have noisy observations, like in the stock market when you read, right? There is no such a thing as a true signal blue in the background, just the noisy version. So what I'm going to do, this is by no means the best. It's a very simple filter. So what I'm going to do, I'm going to calculate the convolution of my noisy signal, let's call it y, that's noisy sine wave, which is really a long vector, a bunch of numbers I generated in Julia. With this vector, k, let's call it kernel, right? There's a lot of things called kernel. So always make every item cooler when you call it kernel. So we call this kernel of the convolution. And if you notice, it's just a 3-vector. It says 1/3, 1/3, 1/3, right? I want to calculate the convolution of this k with this y of t, my noisy signal, and see what happens. Clearly, the output should be, if y is n vector, right, should be n plus k minus 1. Well, because k is 3, it's going to be n plus 3 minus 1. It's going to be n plus 2. So I will have 2 more data points. Now, by now you know that we're going to flip k, right, and then sweep over the signal, and then we just calculate a dot product. Now, but because k is 1/3, what happens is that you will have 1/3 of 3 successive elements of yi, right? For example, you get yi minus 2, I minus 1, and I. And each of them is multiplied by 1/3 because we use the same weights. And then you add them up, so the weights add up to 1, but we're averaging over time. It's 1/3 of 3 time steps to be the output of that particular entry of the convolution. And this is called the smoothened version of the signal. So it's a weighted moving average. So that k is it's an averaging window that moves along the signal. Which is pretty cool because how would you move this window along your signal to do the average? It's not that trivial. You cannot just come up with a simple idea to do that for arbitrary values and numbers. The convolution will do that for you. So the filter signal, you see no, you're not going to get rich with this, Ben, but if you do this on the stock market, you'll probably lose money still. But hey, at least it's smoother, right? So you can see the peaks are like this particular valley here, right? Or this area when it's very sharp, it's just become a smooth line. You could make the averaging window longer, right? Make it 5, make it 10. Or it doesn't have to be uniform, right? Maybe you're weighting the ones in the middle more and then to the sides a little less. Anything is possible. So in filtering and signal processing, this is one application of discrete convolution. You might have heard of low-pass filter, high-pass filter. These are in signal processing. You want to have a filter that gives you low-pass. Low-pass is you will get something like this. If you use a very strong low-pass filter, you probably get something like this. You get basically the core part of the signal that is moving. High pass, however, will give you mostly the high frequency part, right? Something like this. Will it go just up still? Well, you lose the low pass, so it might not go that high. But anyway, high pass will pass all these jitters, but filters this low pass trend. You ready for 2D? Okay, so now I want you to use the imagination that you have from 1D and carry it to 2D. I'm not going to draw so many pictures here. But a 2D convolution is the generalization of 1D. Because matrices are 2D arrays instead of one-dimensional array, which is a vector, we have double sum here. So the output is, so if A is m by n and B is p by q, the output is m plus p, m, p, n, q, right? m plus p minus 1, that's what you would do for vectors, but we do it for each dimension, times n plus q minus 1. So for rows and columns, you will have the exactly same rule. So you have, not only you have to do it for rows, but you have to do it for columns as well. And your moving, basically, window is no longer just a vector, it's a matrix itself, right? So you can imagine a smaller matrix is moving over a 2D matrix, forward, down, right? However you want to calculate it. Now, to avoid confusing people with matrix multiplication and convolution of vectors, let's use this notation, right? Which I got it from Applied Linear Algebra book from Stanford. This is a good notation to avoid confusion with vector versions. With that in mind, let's do. Now, by the way, in the previous examples, I didn't tell you that I am creating my matrix of zeros here, and then I'm looping and filling in the relevant indices using that rule. And the actual convolution happens only here in one line, t times y, right? Try to change this k and see how it will change the result. So now we're going to use 2D convolutions to do edge detection. This is like a very basic example in image processing, digital image processing. 20 years ago, 30 years ago, this was science. Now it's like a toy problem. Now, this is not the best edge detection problem. It has drawbacks. There are better versions, but this is the simplest one we can get. So in image processing, 2D convolution on images, you can think about an image as a 2D matrix. Now you have RGB, but if it's grayscale, it's just a 2D array. If you do want to keep color, you just have 3 matrices, one for R, one for B, and one for G. We're going to work with grayscale images. We define 2 kernels. Of course, they have to be matrix kx and ky. These are called Sobel Kernel. Sobel is the name. Basically, what it's doing is taking the gradient of the image numerically, just like that finite difference that you have. In fact, this convolution and this technique can be used to calculate finite difference as well with careful placement of numbers in your kernel that can be gradient or derivative. So what it's doing is basically, you can see, you have 1, 2, 1. This is along x direction, and this one is along y direction, ky. You have 1, 0. For the first row, you have 1, 0, and -1. Now remember, we're going to flip this, right? When you flip it, it will be -1, 0, 1. So it's going to be, if I is my matrix here, it's going to be I, let's say, I plus 1 minus I minus 1, because the weight of I is 0. Now the difference is just a delta, right? So, and then for the middle one, is weighting them twice as the top row and the bottom row. So it's just calculating the delta along x in the image. The other one is doing the delta along y in the image. When you calculate the convolution, to get the edge, which I write it here, you do 2 convolutions, and then the norm of that, the norm, the magnitude of that delta that you calculated will show you where in the image you have a lot of variations, delta. Probably edges, because that's when the lighting will change significantly and the texture will change, right? Along this surface here on your desk, for the mouse board is similar. As soon as you see the floor or the chair, that's the high variation, high gradient area. And those are the edges in the image. So you need to load and add a lot of packages, test images, which is a list of test images in Julia. You don't have to have an image. It has it for you. Colors and image input-output, I/O. There's another package, Julia Images. I think that's for signal image processing. But we don't need that here. So I added the packages, and I think I should be able to run this. So I'm loading a picture of Fabio. Don't know him personally. It's grayscale, 256 by 256. Fabio, meet the class. Class, meet the Fabio image. So these are pixels, right? Each pixel is the entry of a matrix. You see an image, just think about a matrix. I implemented a function. I call it Sobel Edge. In image processing libraries, you have edge detection. You can choose different methods, right? You don't have to implement this yourself. So I define I input the image, right? Convert my image to be float 64, because a lot of time images are stored as integers. So I'm converting them to be numeric floating point numbers. I define my kernels for convolution. Notice that they're flipped for the same reason that I want to use matrix multiplication. I flip them. I get the size of my input image. I initialize the edge with 0. basically 0 here in the image below is black. The higher the intensity, it will make it white. So now I loop for rows and columns, and each time what I do, I'm sweeping over the image and picking a 3 by 3 block each time, right? I start here. In image processing, this is your beginning always. That's where you start, right? This is 1, 1, or 0, 0. So each time I pick a 3 by 3 block and then move forward by multiplying it. And I do it for x and y. However, it's not matrix multiplication, it's element-wise, right? Be careful. Convolution is not doing matrix multiplication. Which is why if you have GPU, you can just do distributed. It's just a lot of tiny multiplications. You don't need powerful processors, you just need a lot of them. And GPUs are great for these type of calculations. So I calculate intensity or the gradient along x and y in the image. In this line, I'm using ternary operator, which says condition A, B. This means if condition is true, right? Do A, whatever is there, right? Else B. This ternary options, condition, question mark, first statement, whatever you want to do, colon, second. This is really a painless if and else. You just do it like this. Okay. So I'm saying that if, now you see why this agitation might be naive, because I'm saying that if the square root of the norm of the intensity, right? Now, see, you know vector, you know norm, makes it easy. In image processing class, they're not going to teach you norm, right? They say, oh, just take the norm of the intensity vector. You know it already. So square root of norm of I, x, and y. If it's bigger than 100 divided by 255, keep it, otherwise 0. What do I mean is that if the intensity is stronger than certain threshold, keep it. If it's weaker than that, just get rid of it. That will clean up some areas that might not be edge, right? But still they have some gradient. Now, how do you choose this threshold? Probably it's different for each image, the illumination is different, and so on. And in fact, if you try other images, you have to change it to get good results. Why 100 divided by 2055? Anybody has any idea? Let me clear the scene for you.
I don't know why the 100, because I know the 255 because that's like the range of like RGB values for a pixel.
Okay, so you don't know why 100, but you know 255 is the range of the color, the grayscale color here, right? Each of ij entry of that grayscale image is between 0 and 255. Why? It's one way to do it, right? It could be between 0 and 1. If you divide it by 255, right? That's also possible. It's just the resolution you define the grayscale image, right? It could be a continuous value. It could be integers from 0 to 255, right? But it's typically when it's 255, it's because it was integer, right? And the resolution you had, for example, 10 and then 11, right? There was no 10.5. That's a hint for that. Between 0 and 1, probably it could be a continuous range. Why 100? I know that because I coded that. So 100 gave me a good result. That's it. Just try some numbers and see how it works. Again, that's the weakness here because it's not going to work if the illumination changes. So I call my function past the image I, and then they give me the edges. Is this good? Not bad. Could be better, right? But not bad for just a straightforward application of a 2D convolution is not too bad. But this is not how now computer vision engineers calculate edges, right? Let's test how are we doing? Like how fast this function is working. There's a package, it's called benchmark tools. If you add that package, and then I'm using it here, and then type @benchmark, then run your function again. It gives you some pretty results. It took, it draw 103 samples it was drawn, right? Each of them was evaluated once. I think that's what it means, the output. The minimum time, it was roughly 35 milliseconds. Pretty fast. Every second is 1,000 milliseconds. So this was a fraction of a second. The maximum time it took, it was about 75 milliseconds. The median was 50. Anybody knows what's the median here? Unrelated to Rob 101, but I hope you will take the probability and the statistics course. And
I always get median and mode mixed up, but isn't it like the most central? Or like if you cross out everything like on either side, like the one that's in the middle.
yes, the middle, right? Not the mean, right? So because if you have a distribution, not like this, you need to know what is a distribution, right? You have mode, the mean is like this, and the median is, no, where's median? Median is where the mass is actually 50-50, exactly, right? And you have the median, this should be 50, should be 50. But if your distribution is symmetric like Gaussian, right, a bell curve, median and mode are the same. Median is said to be robust to outliers because you always take the middle point. You don't care about outliers, but mean is always shifted. For example, let's say the average income of a roboticist is some X values, right? Should it be mean or median? Mean. Why not median? That's a good point, because I said average, and the average is mean. Because mean is biased, right? If you have some people with very high income and most people making within a reasonable range, right? The mean will be shifted to be more than what most people make. But median is around what most people, the middle point, right? So it depends which one you want to know. Both are different statistics. All right, so that's the median. What about this one? You guys are good at the statistics. It says mean plus minus sigma. So this is mean, right? This is close to median. Plus minus 6.8. What does it mean?
Standard deviation, so how far off?
Standard deviation. How far off from mean? It's the dispersion from mean, right? Now, while that's true, generally speak with your friends, but technically it's not a standard deviation. This is a standard error. What is a standard error? Standard error, because we ran 103 times, right? To get the average mu, mean, was time. So it was the average time divided by 103, right? Add them up, average. Now, this, in statistics, you will learn that this is called sample mean. And this is one type of estimator. It's an estimate of mean, because if you have 10 samples, right? The sample size is 10. It should be very different from when you have 1,000. Shouldn't it be more accurate if you have 1,000? So the standard deviation that you're talking about, the standard error, is the standard error is the standard deviation of the sample mean, not the true distribution. As this 103 goes to infinity, run infinite times, this sigma here will tend to be 0, because you will recover sample mean exactly, right? Now, that doesn't mean the runtime doesn't vary. So this is not the distribution of the runtime, right? It's very tricky, but it's a mistake that happens a lot. I'm not here to answer these questions, but it's very helpful in robotics in general to have a course in statistics and probability. So but the discussion was that you should be able to read this table, right? That's the goal. You see the output, you want to be able to read what you see. Let's try this with coffee. I know this is not coffee in America, but outside of America, this is called coffee. You don't get water in coffee. Espresso. We run the same edge detection, and it works. I chose pictures that it works. If you try other photos and test images, it's not always nice. Now, let me connect it to what's going on right now with modern tools. So the convolutional neural network, what happens is that you have one type which is a fully connected network. For each of the input, you have a weight. There's another type, it's called convolutional neural network. Instead of having a linear model that a single weight for every input, we can use a convolution kernel that goes over the input. The interesting part is that we do not know what values should be inside this kernel matrix, right? For certain task, objective that you have could be edge detection, could be a motion blur, could be finding salient points in the image as features and do some other tasks with it. Then what is a good kernel? So the convolutional neural network will learn this kernel for you. We'll find out what are the right values that minimizes your objective loss function. So that's why it generalized this sort of manual design of features. Plus, you have parameter saving because this kernel is smaller as opposed to having a weight for every single entry. So you learn this convolution kernel of the convolution. And you don't do it one time. For each type, you have many channels. For example, you learn maybe 512 convolution kernel and you apply it to the same image in one layer. You create a bank of filter to get features, okay? So that's what happens in convolutional neural networks. So today you can do edge detection by just running a convolutional neural network. And it will be much more better in terms of performance. There are still classical methods that work really well. Canny edge detection, invented by John Canny. It works really well still. So hopefully now you understand and relate to terms that you hear. Using a convolutional neural network, doing image processing, that's what they do. It doesn't have to be, again, edge detection. It can be generally feature learning, detecting anything in the image. You want to detect if it's a cat or dog, right? You learn a lot of these kernel of convolutions when you have a new input. You pass the image through the network, it calculates all the features, then you have a classifier based on the features, can decide if it's a cat or a dog. That's a modern way of doing classification. So I'm going to finish here and see if you have any questions. This is the end of Rob 101. It's been a great semester for me. I hope it's been a great semester for you too. I enjoyed teaching this a lot. Is there anything you want to ask? Could be from any part of the course or today. General questions, next step, life. Stock market, retirement, Ben?
Would you say out of all the things that we learned, would be like the most applicable to like things we'll go on in the future?
So the question is, out of everything we learned, what is the most valuable part? Right? Okay, I can answer it like this. There is a part of these, so ultimately this course was a linear algebra course, all right? We weren't supposed to program robots here. But we tried to make linear algebra a little more relatable, approachable. So the core knowledge of courses like this, you take differential equations and other math courses, will stay with you for a long time. So now, I expect you to be comfortable when you see vectors, when you see matrices being multiplied, when you see complicated algorithms that do matrix factorization. These things can be very scary to a lot of students. When we do an LU or QR in the middle of an algorithm, and we don't talk about it at all. So your comfort level with these things should be relatively higher than previous generations. What it means, when you take a course, let's say in SLAM, right, robotics, well, we're going to factorize matrices to solve a SLAM, right? If you cannot grasp what it means to factorize a matrix, right, connecting that to a real-world problem will be very difficult. It will be too abstract at that point. So that's one thing. I think that's one takeaway. The other takeaway I would say are the examples we gave you. Project 1 was about linear map and mapping, right? That's a real world problem, robotic mapping. Project 2 was about regression problem, right? And project 3 was about minimum norm solution and model predictive control. People are still doing PhD, getting PhD degree on each of these topics. So these are very important problems to be familiar with, right? And the technical language, I think, that could be a takeaway. And I'm sorry it wasn't as maybe fun as programming a robot, but I know sometimes it's hard to wait, but people used to wait the entire undergrad degree, right? But now we're hoping second year, third year you can take the courses. I know it wasn't a great answer, but partial answer. And again, we had a PhD student in robotics. That student, I know for a fact, that needs to take the exam again because it's just the student is not comfortable with vectors and matrices in Rob 501. For whatever reason, the undergrad degree didn't cover it, right? It's very important. Least squares, right? Half of the engineering is running on least squares. Don't forget that. It's also discipline independent what we cover. You do not need to do robotics. You're set up to be successful in any discipline in engineering. Any easier question? Now, I'm hoping to see a lot of you in Rob 330, fall 2020. It's about Islam and navigation. You won't be qualified to take Rob 530. That's way beyond an undergraduate degree as it is now. 330 is supposed to be that. It's Islam for undergraduate level. Now, you will be able to do a lot of things that they do, but we're not going to bother you with some of the math and harder problems that we insist graduate students to solve. Oh, I forgot programming. Your programming skills was good. Typically, people don't learn math with programming. And that creates a discomfort because when it comes the time to code it, it's just the courage and experience is not there. So I find it, we find it in robotics generally. You will grow much better if program the mathematics that you learn as part of learning. So, SLAM stands for simultaneous localization and mapping. This was a chicken and egg problem in robotics 30 years ago, 20 years ago. We need to know where we are to build a map. We need the map to know where we are. Can we do it at the same time? People didn't know that. Now we know we can. So that's called the SLAM problem. So on Wednesday, there will be Q&A. Professor Griesel and Professor Chad Jenkins, our undergraduate director, will be here. Maybe just me. Maybe just Jesse. That was last year. But generally, let us know how you will do. We love to hear from you as you move up and take the other courses. Let us know how linear algebra and Rob 101 helps you. Things you learn and you think it will be cool to talk about in this course. Let us know about that. And feel free to come and knock on our doors. We'd love to see you again. This is the end of the course, and thanks, everyone. Don't cry. Thanks, everybody in chat.